Hi guys, how's everyone doing? Alright, so today we're here to talk about average and instantaneous rates of change. So the average rate of change of quantity over a period of time is the amount of change divided by the time it takes. In general, the average rate of change of a function over an interval is the amount of change divided by the length of the interval. It's also, if you think about it, it's the change in the y values, the change in the function, over the change in the length of the interval, or the change in the x. That's just a slope. So that the average rate of change can be thought of as the slope of a secant line to a curve. Let's take a look. So here we have a graph that depicts the growth of fruit flies in a lab over a period of 10 days. And we're going to find the average rate of change from day 5 to day 10. So remember, average rate of change is the amount of change over the change in time. So it's the change in the y values over the change in the x values. It's just slope. So our average rate of change is going to be the function value at 10 minus the function value at 5. Since we're going from 5 to 10, it's the function value at 10 minus the function value at 5 over 10 minus 5. Now at 10, it looks like that's where Q is. That height is 12. Minus at 5, that's where P is. That height is 3. Over 10 minus 5 is 5. So our average rate of change is 9/5. So this would be 9/5 of flies per day, because the unit on the function is number of flies and the unit on the time is days. So remember, the average rate of change, ARC for short, is the same thing as the slope of the secant line. Well, what's a secant line? And what happens is, if we take our straight edge, okay, and we connect from P to Q, see how this goes through the graph at 2 points? That is a secant line. So this secant line, if you look at the change in the y's over the change in the x's, okay, the change in the x's, that's this piece here, that's the same as this, which is 10 minus 5. And the change in the y's, that's this distance here, that's the same as this 12 and the 3. But remember, 3 is f of 5 and the 12 was f of 10. So that's why it was f of 10 minus f of 5. So for any given function, when we don't know what the function is, okay, we have this x value here, and it has a matching y value, which we call f of x. We have another x plus h, which has a height of f of x plus h, okay? Now, if I draw my secant line, our slope is the change in the y's here, which would be the y2 minus the y1, or in this case, the f of the x plus h minus f of x, over the change in the x values, delta x, which is x plus h minus x, or just h. And here is our average rate of change formula. And yes, we have seen this in other forms. We've seen this as f of b minus f of a over b minus a. That's also an average rate of change formula. Okay, they mean the same thing. Let's look at an example. So here, we're going to find the average rate of change of f of x, which is 3x squared plus 4, from x equals negative 2 to x equals 1, and illustrate our answer graphically. So to find the average rate of change from negative 2 to 1, we're going to do f of 1 minus f of negative 2 over 1 minus negative 2, which becomes plus 2. Now it's up to you whether you want to do the arithmetic in here, or if you want to come off to the side and say, okay, f of 1 is 3 times 1 squared plus 4. So that's 3 plus 4, which is 7. minus, now f of negative 2 is 3 times negative 2 squared plus 4, which is 3 times 4 plus 4, which is 12 plus 4, which is 16, all over 1 plus 2 is 3. So 7 minus 16 is negative 9 over 3. Our average rate of change then is negative 3. Okay, remember that's negative 3 over 1. Now what we want to do is we're going to say, okay, negative 1, negative 2 is here, and here it is on the function, and we're going to where x is 1, and here it is on the function, and I'm going to get that handy dandy straight edge. And if you look at this secant line, what is the slope of this line? It's going down 1, 2, 3 over 1, down 1, 2, 3 over 1, down 1, 2, 3 over 1. The slope of this line is negative 3 over 1, or negative 3. So to illustrate it graphically, you graph the line and you tell me that the slope is negative 3. Okay, so I have a program here called ARC-IRC and the derivative. If we take a look in the diagram on the next page, secant PQ intersects a graph of f of x is x squared. We want to look at what happens to the slope of the secant line PQ as point Q is moved towards point P. So here's point P, which has x coordinate of x, and its height is f of x. Then we have Q. Its x-coordinate is x plus h, and its height is f of x plus h, just like we saw in our average rate of change formula. Now, what we want to do this time is, if you notice the length of this interval from x to x plus h, that length is h. Delta x is h. As we bring this point Q along the curve, this value, x plus h, is going to get closer and closer to x, which means the length of the interval is shortening, that the value of h is headed to 0. Now watch what happens to the secant line. The secant line is getting closer and closer till right here. Now it's only touching the curve once, and now you don't have a secant line, you have a tangent line. And it doesn't matter whether your x plus h started to the right or started to the left. If I move it, so now I have my point, and if I come from the other direction, it's still, h is still headed to 0, that distance is still headed to 0, and the secant line is still headed towards a tangent line. So now the slope, as the length of the interval approaches 0, the slope of the secant is approaching the slope of a tangent line. Okay, let's go write that down. So this picture is a reminder of what we did on the TI Inspire. So you might want to write here, though, that when you reach that instant in time, so that we're at 1 instant, the secant line is now a tangent line. So the tangents to a curve, basically the process comes with, start with what can be calculated, namely the slope of a secant. So if you have numerical values in a table, the best you can do for the slope of the tangent is to use the smallest interval that you can around the given x value and do an average rate of change. Now, if you have a function, you start with that average rate of change and you find the limiting value of the secant slope as q approaches p. Now remember, that should sound familiar. Limiting value, that's a limit. And we were letting the length of the interval get smaller. We were letting h approaches 0. That's why the slope of a tangent line equals the limit as h heads to 0 of the slope of the secant line. So we define the slope of the curve at P to be this number, and define the tangent to the curve at P to be the line through P with this slope. So this mechanism is the same as saying the limiting position of the slopes of the secant line as q moves closer to P. The slope of the tangent line is the limit as h approaches 0, which is the slope of the slope of the secant line, becomes this instantaneous rate of change, which is the limit as h heads to 0 of the average rate of change, f of x plus h minus f of x all over h, and this is also f prime of x, otherwise known as our definition of derivative. So much there in that little formula. It's the limit of the average rate of change, it's the limit of the secant, it is the slope of the tangent line, it is the instantaneous rate of change, it is the definition of derivative. Let's take a look at a graphical example. So the total sales for a company are shown in the graph below. And the question the first question is the average rate of change of sales positive or negative between t equals 0 and t equals 5? Now remember, average rate of change is the slope of a secant. So from when time is 0 to where time is 5, if I draw my secant line, does that have a positive or a negative slope? It has a positive slope, therefore the average rate of change is positive. Now, is the average rate of change of sales positive or negative between t equals 0 and t equals 10? So again, we draw our secant line, and again, it's got a positive slope because it's going up. Now, is the average rate of change of sales positive or negative between t equals 0 and t equals 15? Again, I'm going to draw that secant line, and this time it's going down, so it's negative. That's this secant line here. I don't know why it drew it pink the first time, so there it is, it's green. Okay, and we have another one like this. Let's try this one. Is the average rate of change of sales positive or negative between t equals 0 and t equals 20? Now you can probably look at this and give me that answer this time without having to draw the secant, but I'm going to draw it, and we can see that it's going up, so again, we have a positive slope. Okay, now we're going to change the question a little bit. Same picture. New question. During which time interval is the average rate of change larger? Between 0 and 5. So between 0 and 5, I'm going to draw that secant line. And then between 0 or 10, so here's 0 and here's 10, and I'm going to draw that secant line again. Okay. Now, if the average rate of change is bigger, that means you're going to want a steeper positive slope. Which one has a steeper positive slope? That would be from 0 to 5. Now, in the next one, during which time interval is the average rate of change larger? From 0 to 10. We already have that drawn. And from 0 to 20, so here's 0, here's 20. I'm going to draw that secant line. Which one has a steeper positive slope? That would be the second one, from 0 to 20. Now we want to estimate the average rate of change between 0 and 10 and interpret our answer. So we would have to do, in order for the average rate of change, we would find the sales at time 10 minus the sales at time 0 over 10 minus 0. It's the change in y's over the change in x's. So at time 10, it looks like about 750 in sales. It's an estimate. So as long as you're close, we have similar answers. I'm more worried about the process right now than the actual answer. And S of 0, that looks like it started right there at 500. Over 10 minus 0 is 10. So this is 250 over 10. So that's 25. Now don't forget your units. The units on S is sales per, the unit on the time was weeks. So 25 sales per week. That would be our average rate of change. So now interpret it would mean during, because from time 0 to 10, so during the first 10 weeks, sales, now did they increase or decrease? So since this was a positive rate of change, sales increased at a rate of 25 sales per week. Okay, let's look at one that has both an analytic and a numeric component. So here, At an excavation site, the amount of dirt that has been removed in cubic meters is modeled by the function f defined below. G is a differentiable function, and t is measured in hours. Values of g of t are given in the table below. According to the model f, what is the average rate of change of the amount of dirt removed over the time interval from 6 to 12 hours? So average rate of change. Now the function for removing the dirt is f of t. So we would do f of 12 minus f of 6 over 12 minus 6. But when you look at the function f from 6 to 12, it's on that bottom piece of the function. So in all honesty, if you started right here at this step, that's also okay. So g of 12, that's 474, minus g of 6, that's 306, over 12 minus 6 is 6, and if we do some subtraction, we're going to get 168 over 6, which is 28. So our answer here is 28. Now don't forget the units. The change in the g's, that's cubic meters per, and the change in time, that's hours. So 28 cubic meters per hour. Same problem. This time, we're going to use the data in the table to approximate f prime of 9. Now 9 is in this interval from 6 to 12, which means we're using the function g, okay? Which means we're using this table. But 9 is not in this table. 9 is somewhere between 8 and 12. So in order to approximate the derivative at 9, we're going to use the smallest interval we can around 9. So we're going to go from 8 to 10. So we're going to find g of 10 minus g of 8 over 10 minus 8. Okay, so 10 minus 8 is 2. The denominator is easy. Now the top, g of 10 is 428. Minus, and the g of 8 is 376, so if we subtract, that's going to give us 52 over 2, which is 26. So again, 26, don't forget the units. The change in the g's is cubic meters per, the change in the time was hours. So 26 cubic meters per hour. Okay, same problem situation, only this time is f continuous. Now here's the thing, before we get started, f is in two pieces. And if you look at the top piece, from 0 to 6, if we just look at that piece, f is continuous on that piece because it's a cubic function, right? Continuous, since it is a polynomial function. Also, from 6 to 12, f is continuous since they told us here g is differentiable. Since g is differentiable, which means g is continuous on the interval. So the only problem we have to check is where it's changing pieces, which is at 6. So the first thing we do for continuity is we find f of 6. Well, f of 6, they give us, we would use the bottom piece of the function, which is g of 6, which is 306. The function exists. Next up, we're going to check for a limit. So we do the limit as x approaches 6 from the right of f of x. Now if we're to the right of 6 on the number line, we're using the bottom piece of the function, which is just g, which becomes g of 6, which we already said is 306. Now, if we do the limit as x, or actually these should be t's, limit as t heads to 6 from the left of f of t is the limit as t heads to 6 from the left of the top piece of the function, 48t plus t squared minus t cubed over 12, which is going to be 48 times 6 plus 6 squared minus 6 cubed over 12. Now let's do some arithmetic. 288 plus 36 minus 18 is 306. These numbers are the same. Therefore, the limit as t heads to 6 of f of x is 306. So finally, the third step is that the limit as t heads to 6 of f of x is f of 6. So therefore, f is continuous for 0 less than equal t less than equal 12. And yes, guys, it is important that you make those two statements at the beginning so they know you're recognizing the only place you have to check with the 3 eyes is at 6. All right, we did a lot of stuff today. Take a look over your notes, come to class with questions, and we're going to practice some more. Have a great day, everyone.